So let's begin by talking about the addition of hydride reagents. So here's the general reaction, but it comes with a caveat here, is that you have a hydride in quotation marks as your nucleophile. And this hydride attacks the carbonyl carbon because it's electron deficient. And of course, they break this pi bond. You get to oxygen with the negative charge. And then what happens is that you have protonation, you protonate this oxygen, and you end up with an alcohol. So this is the reaction pathway. However, we put this hydride in quotation marks because what we're trying to tell you here is that in solution for this reaction, hydride does not come in this form. It's not like a nucleophile, an ion that is floating around. It comes in a different form. So this one is not entirely true. So what is the hydride source? It's sodium borohydride, NaBH4, lithium aluminum hydride, LiAlH4. Shown you this before, but it's not sodium hydride. So you might think, sodium hydride, Na plus, H minus would be a suitable one to use. Problem with this is that this one acts as a base. And not a nucleophile. So hydrides in their free form are excellent bases, strong bases, but they do not exist as nucleophiles. So where do they come from? They come again from sodium borohydride and lithium aluminum hydride. So let's look at sodium borohydride. So sodium borohydride would be surrounded by 4 H's. It has a negative charge, formal charge. And of course, the sodium is the counter ion, so it would be sodium. I'm going to put it here on the top. We usually don't show it, don't include it, because we're focusing on this. There's an important thing to mention here is that the electronegativity of boron is 2, and the electronegativity of hydrogen is 2.1. So in this case, the hydrogen, in a sense, gets the delta minus, and the boron gets the delta plus. Now, this is interesting because, again, you're thinking about the minus on it here, but you're talking about two different things. You're talking about electronegativity, and here is the formal charge. So you can see that this is, the hydrogen has the upper hand in terms of the electron density. It's pulling electron density toward it. It's worth mentioning something about this before we move on, is that this is only reactive, or only reacts with aldehydes and ketones. This is very important for you to remember. So it's selective. Now, on the other hand, lithium aluminum hydride so that would be Al minus. So once again, H has at 2.1 electronegativity, and the aluminum is actually 1.6. Let me bring this down a little bit. So once again, this is delta minus, and this would be delta plus. Let me remove this negative from here just to simply talk about the polarity difference here. So you can see here that the aluminum is much less electronegative than hydrogen. And therefore, this makes a huge difference between using, again, aluminum hydride versus sodium borohydride, or borohydride here. What happens here is that if this is less electronegative, what ends up happening is that this would leave the hydrogen in the aluminum substance here, in the aluminum hydride, with a greater concentration of negative charge. So which makes it more reactive. The hydrogen is much more reactive here because it has more electron density because of the difference in electronegativity. Aluminum is nowhere near as strong as, let's say the boron here. It's 1.6 versus 2.0. So again, more electron density will be on hydrogen in the aluminum hydride versus in the sodium borohydride, which makes it again more reactive. It's important to say that this reacts with all carbonyls or with both types. So let's say reacts with all types, all type 1 and type 2 carbonyl compounds. As we say here, this one reacts violently with water. That's why it has to be, you have to use dry solvents and you have to quench, meaning you add water very carefully. You add a drop at a time. So let's look at a typical reaction of carbonyl, and we're going to draw the mechanism for this. So make sure you're ready yourself. So we did show you this mechanism before, but not in a general form. So we have an aldehyde here. We have lithium aluminum hydride. So let's look at the mechanism. So here's the aluminum hydride. Which, by the way, lithium aluminum hydride is sometimes written as LAH. So if you ever see that, that means the same thing, lithium aluminum hydride. Very well. So it has a negative on it. So remember, we don't have hydride on its own. We're going to take this hydrogen and its 2 electrons in this bond and move them or make them attack the carbonyl carbon. So we have now CH3. We have the carbon in the middle. We have oxygen. Carbonyl oxygen now, it's no longer double bonded. It's single bonded with a negative charge. We have the hydrogen. right here. And of course, we added another hydrogen. That's the hydride that you added, this one right here. So notice, I'm going to show you just for now so you can see the movement. This is what moved right here. So then the next step would be is if you have water, then that can only indicate that this is needed for protonation. And you would get your alcohol product. So I'm showing you everything here so everything should be accounted for. So remember, this is irreversible. Can't kick out a hydrogen once it's added. And once again, it's worth mentioning that this was an sp2 carbon. Now it is an sp3 carbon, hybridized carbon. So you started with an aldehyde and you ended up with an alcohol. In this case, it's a primary alcohol. So even this one is also irreversible. It's simply waiting for it to be protonated. So that's the mechanism. So let's look at now another mechanism where we use sodium borohydride. There's no difference in the mechanism except now you're replacing the aluminum hydride with the sodium borohydride. So the movement of the arrows is the same, but we have a ketone now instead of an aldehyde. But again, it's not going to change the mechanism. So we can take this. You should pause probably and draw the next part. It's really nothing different, except now you have ethanol as a solvent instead of water in this case. After it. So you should now be getting the CH3. The other CH3, and then we added an H. Remember that. So now the next thing would be you can arrange it this way. Again, you're doing the protonation here. And now you have a secondary alcohol. It's worth mentioning. So notice again, you started with a ketone. You have 2 carbons attached to that carbonyl carbon versus 1 here. That's why you had a primary. So patterns are very important in this class. We need to be able to pick them up really quick. There's just a few things I needed to mention. So you might be asking, well, what's left over? Then you'll have BH3. You'd have OET minus. They would actually be in one compound if you look at the mechanism, but all of these are just byproducts. We don't care about them. The other thing, and then you would have the sodium. The other thing that I wanted to mention is for both is notice what's happening here. Okay, you had a reduction. There's a reason why it's called a reduction. So in the reduction here, what happens is that you had a loss of carbon-oxygen bond. It was a double bond. It became a single bond. And you had a gain of carbon-hydrogen bonds. That's called a reduction. An oxidation would be the opposite. Of course, not only confined to oxygen, but you would have also, let's say, halogens as well, or even nitrogen. But that's why it's called a reduction. So we went from having a carbonyl carbon oxygen double bond to carbon oxygen single bond, but also a carbon hydrogen single bond. That was the change. So that would be a reduction. A few things before we end this video is that sodium borohydride only reacts with aldehydes and ketones, as we said, and the reaction is typically run in an alcohol solvent. So a second protonation step is not needed. So a second protonation step is not needed, meaning you can actually, this will take care of it all in one step without actually doing, let's say, another step, meaning all of this, notice I didn't list this as 1 and 2. I did not do that. I just simply said I'm doing them all in one step. So then the solvent would, this is your solvent, would act as the source of protons for this reaction.